Hello, my name is Callum Patterson, and this is my 4-bar mechanism that I designed for elbow rehabilitation. So, for a bit of background, the radial head slash neck fracture you can see in the X-ray there, which bones I'm talking about, is a break near the elbow joint in the radius bone. It's commonly caused by falling on an outstretched arm, so that could be sports injuries or any kind of trauma. Symptoms will be same with any kind of broken or break or fracture. Pain, swelling, limited motion, and quite stiff. So the goals of the therapy is to restore that range of motion, is to prevent the stiffness, and to gradually increase the muscle strength so you can get back to the strength of the muscle and the joint flexibility that you want to have. Passive motion therapy will assist the movement so the patient can get back to that initial range of motion. So the 4-bar mechanism that's proposed is a mechanical system with 4 rigid links, which are connected by pivots in the 4-bar. It will mimic the natural joint motion to guide elbow flexion and extension. Wire 4-bar mechanism is very simple and you can make it easily adjustable and it will mimic the joint articulation. So the design of the mechanism, the first link is the fixed frame, that's the stationary link, and that will go on your upper arm. The second link is the input arm, which is the crank that's driven by the hand or the motor to move the elbow. The output arm attaches to the forearm, and the coupler will attach the input arm to the output arm, allowing it to guide the elbow. So here's the sim that I got in Fusion 360. You can see the stationary link, green, where it sits on the arm. And Grashof theorem, if one link is a crank which rotates continuously, then it's talking about the length of the links. So here is my diagram in Fusion 360. You can see the lengths of all of the arms in the browser. And you can see the crank rotates 360 degrees and it brings up the output arm, which is where the forearm will be, all the way up to the top, and then it will go back down all the way to the extension. So here we have the kinematics of the 4-bar mechanism. Going back to Grashov law, it ensures continuous rotation if the length of the shortest link, the input link, and the length of the longest link, the coupler, are less than or equal to P and Q, so the length of the stationary and the output. So you can see my length here, 160 millimeters is less than 180, so the condition is satisfied. Here we have the position equations, so where S is the input link, L is the coupler link, P is the output, Q is the stationary. The input crank, theta 2, is what drives, that's the angle that drives the mechanism. So differentiating these position equations with respect to time gives velocity and the speed at which the forearm moves when the mechanism contracts. And then taking the time derivative of the velocity equation gives the acceleration of the forearm, so how quickly it will contract. These numbers are important because it will ensure smooth motion, so it's not completely uncontrolled, and it doesn't damage the elbow further. So prototype construction, I use cardboard, but for a more advanced prototype you could use wood or plastic. The assembly needed something to connect the pivots and the links securely so that it doesn't fall off. And then in the final prototype or the final product, you would need variable length or angle for different size patients and different therapy processes. So to showcase my prototype, you can see the fully extended part on the left. That is where the arm is fully extended, and then full contraction is on the right, and that will be peak contraction for the arm. Here is a video of me wearing the arm. You can see peak contraction and peak extension, and the input length, which will rotate fully around the joint. In conclusion, the 4-bar mechanism is a very effective therapy tool. It will assist the elbow rehab through guided motion. It's a very simple mechanism. That prototype was easy to build, and it's easily made adjustable for patients' need. The mathematical validation gives safe and accurate motion. The future work would be to improve the adjustability and to integrate sensors for quicker feedback. Thank you for listening.